Welcome back. In this lecture, we will discuss the surface states, band bending, and band alignment at the surface, and also metal semiconductor interfaces or metal semiconductor contacts. This surface for transport on the surface or transport into the surface or across the surface plays crucial role in low dimensional systems. Just to illustrate the importance of surface, I have considered in this case a 1 centimeter cube of some material. Assume that it's a crystalline material which has a total of 6 centimeter square surface area. The moment you chop that into 1 millimeter cube, the surface area will increase to 60 centimeter square, which you can calculate simple mathematics. And if you chop that down to nanoparticles, something like 1 nanometer cubes, then the total surface area will be close to 1.5 acres. So the surface to volume ratio is an appreciable number when you consider low dimensional systems or low dimensional transport. And the characteristics of the surface, the behavior of the surface, the quality of the surface interface, these play a major role in low dimensional transport. Just to give you an example on the surface to volume ratio, 1 kilogram of particles of 1 millimeter cube will have the same surface area as 1 milligram of particles of 1 nanometer cube. So if your technology that requires large surface area, such as various catalytic activities, then nanoparticles or small dimensional system with large surface area will play beneficial role to your application. But that is not going to be the main focus for our discussion. What we are going to discuss is how these surface play important roles, mostly detrimental roles for our transport, because to inject and take electrons or current into and out of the system, you always have to cross the surface. And how good the surface need to be, or what are the characteristics of the surface which actually beneficial for us or which are basically detrimental for us. These are the main points that we will be addressing in this session. All right. Now, let's compare quickly the surface and the bulk. What I have here shown. Now, let us compare the electronic states of the bulk, the solid, and the surface. In the bulk solid, what we have is a regular array of atoms or regular array of lattice points. And when you reach the surface, you are going to break that symmetry, and because you have no lattice points or atoms on this side, and what you will end up is getting a lot of unsatisfied bonds or dangling bonds. This will change the overall potential landscape as you move close to the surface, and there will be rearrangement of these atoms and all those other details which we will not address. But to put it in nutshell, or put it briefly, the potential seen by an electron as you move towards surface or at the surface is different from that in the bulk. And so these states at the surface are very different from the states at the bulk. So the band structure calculations that defines the properties of the solid, they don't take care, or they don't consider the surface states. And assumption there is the solid is a continuous medium with extents from minus infinity to plus infinity. It doesn't take care of the surface. So the illustration here shows that you have a regular array of atoms, and these are the potential due to that lattice points or sites. And suddenly there is a huge potential barrier. And in actuality, it is not like a step function. You can consider it's most like a kind of rather, smooth rise into something very high in potential, or you can say almost close to infinity potential, because the electrons cannot exist there. These electrons cannot go there. So you can consider the potential outside solid is infinity. And in that is a premise that we also did the particle in a box problem in the one of the previous lecture. Okay, now these states of the surface can be of intrinsic or extrinsic. They can be caused by the native bonds which are broken, or they can also caused by some other particle sitting on the surface, such as some impurity atoms, adsorbed atoms. All those things can actually contribute to electronic states at the surface. And the nature of the surface states is very different from that of the bulk. In the bulk, the states are defined by the Bloch theorem, and which you have done in the solid state physics course, I assume. And these states are for a periodic distribution of lattice points, satisfying the Bloch theorem. Those are Bloch functions. Whereas the states of the surface decays exponentially. Okay. This bulk states, as it reaches the surface, it will decay exponentially. But then the surface will have states. As I told, these states can be intrinsic or extrinsic in nature. These states does not exist in the bulk either, because the potential condition for the bulk is different from that of the surface. So these surface states, which exist only surface and maybe to some distance, some penetration length into the bulk, those states generally exist in the forbidden gap, because those doesn't belong to conduction band, or those states doesn't belong to valency band, and the only place they can fall now is the forbidden gap. So these states, which doesn't exist inside the bulk of the solid, or exist only in the surface, they fall in the forbidden gap region in the energy band diagram. Okay. But now you may ask, are these extra states? Actually not, because the number of states in the solid come from the number of states in the constant atoms, and you are not adding or removing any atoms. The total number of states will remain the same. Okay. So now the surface states are actually some of the states which are supposed to be here in one of these bands if we didn't have a discontinuity. But since we have chopped the solid and creating surface, those states will fall in the forbidden gap region here. Okay. So in summary, what we have learned is there is surface. The surface play a crucial role in transport, and the states at the surface are different from that of the bulk, and these states exist only at the surface and decays as it goes into the solid, and these states or energy of these states fall in the forbidden gap region. Now, one more point which I want to mention here is the third point here, that is the surface states can actually take or donate electrons. You can have a bond, just to put it very simply, you can have a bond which is broken, which has that extra electron or which can actually take an extra electron. So you can find the surface states in either in a condition where you can donate an electron, or it actually can capture an electron or accept an electron. Okay, so you can have two kinds of surface states too. So in this premise, we'll move ahead and look into what are the effects of these surface states for our normal electronic transport in low dimensional systems. All right. Now, as I just mentioned, there are two kinds of surface states which are broadly classified as acceptor-like and donor-like. So these acceptor-like surface states are those, they are neutral when they are empty. They can accept an electron from the conduction band and get negatively charged. Those acceptor-like state are close to the conduction band in energy. This is the conduction band, and this is the valency band, and this is the Fermi level. So these states lie close to the conduction band and capture an electron from the conduction band and become negatively charged. So those states are called acceptor-like, and remember, they are neutral when they are empty. That is how it is defined. Now, there are donor-like states. Those are neutral when they are filled. That means they have the electron, but they are actually neutral when they are filled. So these states can donate the extra electron. It's not an extra electron, it's actually neutral to start with. Now, it actually can donate the electron to valency band. And these states are close to the valency band. They can donate electron to valency band. This acceptor can capture electron from valency band. This actually can donate electrons to valency band. Okay, so these are donor-like and these are acceptor-like. But if you look carefully, both of these states are actually not good for us, because in the conduction band you actually need electrons, but these states will end up capturing those electrons from the conduction band. In valency band you actually need holes, but these states will end up removing those holes by neutralizing those with or giving electrons to those states. In either case, these are not really good for us. Okay. Now, what happens is, as it captures electrons from the conduction band or donate electrons from the valency band, these states will get charged. In one case, donor-like is neutral to start with, but then they will donate electrons to the valency band and they will get charged positively. The acceptor-like states are also neutral to start with since they are empty, but they capture electrons from the conduction band and they will get charged. In either case, the action of these surface states is basically transferring charges from the bulk to the surface. In one case, it is a positive charge. If you start with a p-type material, then you have a lot of holes, and these holes will, get neutralized, or these states, donor-like states, will donate electrons to the valency band, and these states will be positively charged, or the surface will get positively charged. That is the result, and the bands will bend downwards for a p-type. By similar logic, the acceptor-like states will capture electrons from the bulk. Remember, this band diagram I have drawn is for the bulk. Okay, and the surface will get negatively charged, and these bands will bend upwards for n-type at the surface, and these bands here will bend downwards for a p-type material. In either case, what you are going to have is an alternation in the band structure or alteration in the conduction band or valency band profile as you move closer to the surface. But all of our physics, all of the transport that we have explained based on the band structure of the bulk. But remember, without crossing the bulk, you cannot get into without crossing the surface, you cannot get into the bulk. So understanding this band bending because of the surface states is really, really crucial to carry out any of the transport measurements. All right. Now, here we will try to do a very simplistic approach and calculate how much bending is there in the band as you reach the surface. I have here a diagram, a sketch which shows a rough distribution of charge as the band is bending. So what I have here is a region which is positively charged. That happens because as you reach the surface, let's consider this n-type case here. Remember, is here, n-type case. Remember, the band is going to bend up because electrons from this region has actually been gone to surface, and you have exposed positive ions, and these ions are actually donor ions because the electrons are coming from the donor atoms. That is our assumption, and this is an n-type material. So you have exposed donor ions, those are positively charged, and that is what we are representing here with these positive ions. And these electrons will go onto the surface of the material, and that is going to give you a negative charge at the surface, which I have represented here. This way. So you have a negative charge, a sheet of negative charge at the surface, and a depletion region, which are the positively charged ions. If Nd is the donor density, which you can control, which you can define, and you can also assume that most of the donors are completely ionized, then the surface density, so the electronic concentration of the surface is given by Nd into the depletion region. Okay. So by a simple rearrangement of these terms, you can see that the charge density at the surface is carrier this donor density into the charge of electron. That is the charge density. And that is again given by this equation here, which we already have discussed. Now, the Gauss law we can use to understand how much of a shift is there in the band structure, or how much of a potential change is there as you reach from the bulk to the surface. So this is your Gauss law, which is the second derivative. This is in one dimension. In one dimension. So d square v by dz square, where z I have assumed as the axis which is running normal to surface into the material. Okay. So now the equation for the potential along the z direction you can get by integrating this, and that is given by this relation here, and we have assumed the 0 point is the surface. Okay, then the potential is given by minus ENT epsilon naught epsilon r z dub, where z dub is the depletion length. So what you are seeing here is depletion length is the place where the potential of the bulk, the potential of the, or the energy of the band is basically assuming that of the bulk energy, or somewhere here, I would say. So from the region z dub, point z dub onwards, the band is going to bend upwards. That's what we are seeing here. So what this equation is telling you is, if you start with an n-type system, n-type material, you are going to have a band bending in the upwards direction as you reach the surface. Now, in a similar way, we can also show that for a p-type material, the band will bend downwards for a p-type material, which is easy to show. Okay, so the overall effect is the transfer of electrons, or transfer of charge carriers, electrons or holes, from the bulk to the surface to satisfy those states, which will end up charging the surface and also altering the potential landscape of the conduction band and valency band as the electron, or as the band reaches the surface. That is the effect of this surface state. Here we will discuss a neat trick or a technique where we are utilizing this band bending for gating applications. Usually, gating is done by the deposition of a metal surface onto a semiconductor, but with an intermediate layer of oxide. But here, the idea is the depletion region, which was created by the band bending, will replace the oxide. So there will not be any oxide at all. We are going to use this depletion region as the non-conducting region, similar to oxide. The advantage is you don't have a rough oxide surface, and we can directly put the metal on top of the semiconductor. But again, this doesn't work for all kinds of semiconductor. You have to choose the semiconducting material and the metal surface appropriately. Okay, so the technique goes like this. You have a semiconductor and you have metal on the surface semiconductor. The semiconductor will have band bending, as we described, and that is going to create a potential barrier when you look from the metal side. But this is the Fermi level for the metal. So this is where you have the metal Fermi level. Okay. Now, what's going to happen is you have a potential rise as you move close to the surface. Okay, that's what you're going to have. Okay, so now this potential rise is given by this equation. Okay, that's what you're going to have. Here is the Fermi level. Okay, and as you go from the semiconducting bulk to the surface where the metal is deposited, you have a potential rise that is given by this equation. Now, the potential barrier seen by the electron is given by this quantity where you multiply that potential by the electronic charge. And you can calculate what is the depletion region or the depth of the depletion region or extension of the depletion region into the semiconductor by inserting this in this equation, and that is given by this in terms of the potential phi b. Now, this phi b can be modulated or changed by the application of a voltage onto this metal. So, the effective potential seen by the electron is a combination of this phi b and the voltage applied on the metal. Okay, and so the depletion length now is a function of the voltage applied. It's also a function of the phi b, but that is a constant for a given choice of semiconductor and metal. So now you can modulate that depletion length, how far you have that non-conducting region into the semiconductor by the application of voltage. So now, just to demonstrate the idea, what I have here is a cartoon where I have a semiconducting surface or semiconducting material, and I have a metallic surface which is created by the deposition of some metal on top of the semiconductor. Okay, initially when there is no voltage applied, let's assume that the Fermi level, the conduction band, when I run from the one end of the semiconductor and other end of the semiconductor across the surface is flat. Okay, now by the application of the voltage onto this ring-shaped representative metallic gate, I can extend the depletion region down underneath this gate. Okay, so that is equivalent to saying that I am actually rising the conduction band wherever I have the metal deposited, or I am actually modulating the profile of the conduction band, or I am actually engineering the conduction band profile or landscape inside the metal. This is actually a three-dimensional. There is a three-dimensional profile to it, because remember, this is a line cut along one of this direction. Now, when you look from the top, what you're going to see is a ridge-shaped conduction band profile when you look from the top. In this case, that's what you're going to see. Okay, so just by application of voltage onto a metallic gate, you can actually modulate, or you can actually change the profile of the conduction band inside the material. That is possible because you are changing how far this depletion region is being extended into it. Okay, and this is a very effective technique, and most of the devices that we are going to discuss during the course of this lecture is defined by this technique called Schottky barrier gating. Generally, most of the quantum devices are gated devices, and this Schottky barrier gating is a technique which is widely used for various devices realized on two-dimensional electron systems, which will be a major topic of our discussion during the course of this series of lectures. Okay, now you can also say that this phi b is the built-in potential. Even if you don't have a voltage on a metal, you still have the phi b there. Okay. So that phi b is going to give you already a conduction band profile even without application of a voltage. Okay. So if you consider the profile without application of voltage, you still have few, millivolts of bend in the conduction band profile. For example, in the specific case for a gallium arsenide material with this given electronic configuration, you have a depletion strength of 60 nanometer even when you have no VG or the gate voltage applied onto the metal. What that means is, within a depth of 60 nanometer, you have profiled the conduction band into this annular shaped or ridge shaped region. Okay. And this table here summarizes how much of this Schottky barrier heights or these barrier heights for a combination of various two major semiconductors. One is a gallium arsenide, N-type gallium arsenide, and N-type silicon. So for example, the gallium arsenide with the hafnium is going to give you very large, close to like 0.75 electron volt in the barrier height. Okay, and gold is also pretty high, is close to 0.9, and platinum also. But for example, for silicon also, you have aluminum close to 0.6 and silver slightly higher, and gold somewhere here, and platinum somewhere here. So what you're seeing here is an interesting story. That is most of the commonly used metals such as gold, platinum, aluminum, with most of the commonly used semiconductor, that is silicon N-type and gallium arsenide N-type, they all give barriers. That means if you try to inject electrons through these contact material, you always have to cross over this barrier to get into the surface. Okay, because you are trying to, if you put directly metal on top of semiconductor, this barrier will be always there, and this plot is going to give you the value of those barriers. Okay, and the point here is, if you try to inject electrons through the leads made by these metals, there will be always this barrier coming into picture, and you have to cross this barrier to get into the semiconductor all the time. That is the take-home message, and that is our discussion for next couple of slides. All right, now we will discuss metal semiconductor junctions. Now let's continue our discussion on the metal semiconductor interfaces. Okay, and these interfaces are really crucial. The characteristics of this interface are very important for our transport studies. Okay, so now let's consider as a first example an N-type semiconductor and a metal surface. The semiconductor side is represented by these energy levels of valency band, Fermi energy, conduction band. Fermi energy is close to the conduction band, is an N-type semiconductor, and phi s is the work function, and chi is the electron affinity. And the metal side has Fermi energy EFM, and phi m is the work function, and you have the vacuum level, which is the reference here. Okay. So condition here is the phi m is far greater than phi s. That's our starting condition. And here, this diagram refers to how the bands are going to get aligned when you match or when you bring this metal and semiconductor together. The band is going to bend upstairs, and you'll have a depletion region, as I discussed. Okay, and the Fermi level for the metal is here, and there is a built-in potential given by this phi m minus phi s, and the potential barrier is given by phi m minus chi. Chi is the electron affinity here. Okay, and ZW is the depletion region, metal side and semiconductor side. That's the picture we have. Now, as we saw in the previous lecture, sorry, previous slide, we have a barrier phi b when I try to put electrons from the metal side into semiconductor. Now, what I am interested is, what is the behavior of this junction when I apply voltage across it? How does the current is going to change? How does the current change? How will the current change when I apply voltage? So let's consider the first reverse bias case where the negative voltage is applied to the metal, positive voltage applied to semiconductor side. So the application of the voltage, positive voltage will lower the band, tilt the band, okay, downwards, or lower the bands on the semiconductor side with respect to metal side. And what you are going to have is, when you lower it further and further and further, this point will be here, but you will get thinner and thinner and thinner, and you will start getting current across this ring, across this barrier, and that is represented by this rise in current here. So because of the thick barrier to start with, the barrier is thick to start with initially, okay, and when you lower it further, that barrier is going to get thinner, and you also have higher voltage too, okay. That will result in a nonlinear behavior. The current will rise. Okay, now let's consider the other case, forward bias case, where you are applying a negative voltage onto the semiconductor side with respect to the metal side as a positive voltage. Now the action here is, you're going to rise this barrier, sort of rise this barrier, and because you are rising overall conduction band profile on the semiconductor side. Okay, in this case you will have no serious or no significant rise in the current, and it's going to be flat, because as you increase or reduce the voltage more and more, or increase the magnitude of the voltage in the negative direction, what you will have is, you are making the barrier thicker and thicker, making it higher and higher, so you will have no current flowing through in the reverse direction, sorry, in the other direction. That is forward bias case. Now, this behavior is like, you have current flowing through in one direction, but other direction there is no current flowing through. So what you're having now is a rectifying contact, or you have current flowing only in one direction. Okay. Now let us consider the opposite case, where the work function of the metal is less than that of the semiconductor side. The semiconductor band diagram remains the same, but the metal that you have on the semiconductor has a lower work function. And this is the cartoon representing the band bending at the interface. Here let's consider the forward biased case and reverse biased case IV characteristics. In the reverse bias case, you have the positive bias on the semiconductor side with respect to the metal. Semiconductor is n-type, and the forward bias case, you have the negative polarity on the n-type semiconductor side. So in the reverse bias case, what you are doing is, you are lowering the band structure, or the conduction band, and the forward bias case, you are rising the conduction band. In both cases, the electrons can freely flow to the semiconductor and from the semiconductor respectively. This is for the reverse bias case. The electrons will flow towards semiconductor without any barrier, unlike the case for the Schottky behavior. So the current will rise as with the voltage, applied voltage. And in the forward bias case, the electrons will flow to the metal side. And in that case also, you have no barrier. The current will rise in the other direction also. So you are going to get a nearly ohmic behavior in this case. So what we have is an ohmic behavior in the IV characteristic when phi m is less than phi s. When the metal work function is less than that of semiconductor and the semiconductor is n-type. In the previous case, what we had is a Schottky behavior, and that is something which looked like this. You have, and the current will never go up. This is flat. That is your Schottky, and this is the ohmic. So in general, you can say that n-type semiconductor with phi m less than phi s is ohmic. P-type semiconductor with phi m greater than phi s is ohmic. These two are the guidelines. And p-type semiconductor with phi m less than phi s is rectifying. Similarly, n-type semiconductor with the phi m greater than phi s is also rectifying. So this general guideline will tell you what metal to use on what semiconductor depending on the doping level and also the work functions of the metal and the semiconductor. But again, I just want to caution you here that there is nothing called pure ohmic behavior for metal semiconductor contact, whatever is the case. But you can always approximate ohmic for small bias or low bias regimes, because you don't have a completely linear potential landscape, whether in this case or in this case. So when you apply higher voltage, you are going to generate non-trivial transport mechanism, which are not topics of our discussion here. We are interested only in linear transport regime where the current is studied as a function of low voltage or in the low bias regime. All right. In the next lecture, we will look into semiconductor interfaces and how the bands are going to bend when you sandwich two different semiconductors, and how are you going to get the two-dimensional electron system at the semiconductor or the interface between two semiconductors. Okay. Now that we will discuss in the next lecture. All right.